Today we're going to start section 1.2. We'll finish it up next class period. And what we're going to look at today is patterns. Several different kinds of patterns, actually. When I was in graduate school, my research project to graduate my dissertation, that big giant paper you've heard of people writing, something so called a thesis when you do a master's project, actually had two people that I was working with, and I asked them to define mathematics. And one of them defined mathematics as the study of patterns. And that is one of the real big ideas in mathematics. So that's what part of this section is sort of lending itself to, is that idea. We need some vocabulary first so that when you see it in questions, you know what they're asking you for. So the first one is conjecture. A conjecture is simply a statement or a conclusion that has not been proven. So in science, you sometimes will call this a hypothesis, right? It's what you think is going to happen. What you think is going to happen. A counterexample is something that shows the conjecture is false. It's an example counter to what we thought was going to happen. There are two types of reasoning, and you've used both of them before. Inductive reasoning is a method of making generalizations based on observations or patterns. Right? So it's what you do when you wake up in the morning. You didn't check the weather. You just said yesterday and the day before and the day before and the day before it was about this degree, so I think I'm dressed appropriately and I go outside. Right? You're making a generalization based on a pattern of what you've been seeing happening. Right? So when all the little children come into your classroom semester after semester, year after year, and none of them know how to tie your shoe, you make a conjecture that the next group of kids is going to come into the classroom and none of them are going to know how to tie their shoe. Deductive reasoning is sort of the opposite, and that's the mathematical part of what we see happening here. This uses mathematical axioms, theorems, definitions, or undefined terms assumed to be true, and logic for proof. And I'll show you an example of when that happens so you can see what that looks like. Okay, and you'll be like, oh yeah, I've done that before too. But an example will help written down. Okay, a little bit more vocabulary. Does everybody have this one written down? And there are several things to write on that slide. Are we good? Okay. Sequences. Sequences are an ordered arrangement of numbers, figures, or objects. So no matter what age kids that you work with, even the tiny little ones, sequences come up. Usually with the youngest of children, they come up the first time with things like, you've got pictures, images, shapes, and it shows something like red triangle, blue square, red triangle, blue square, what comes next? It's a sequence. It's a sequence of objects. As you get far enough along, you start looking at patterns of numbers, and we actually saw some of this happen with Gauss last time, and that's why on that one problem we looked at it and said, oh, that 13 should not have been there, right? It wasn't in the pattern of what we were expecting. Okay, that's what a sequence is. A recursive formula is a formula based on the pattern that is established after one or more consecutive terms are given and a rule that shows how to obtain each successive term of the sequence. This is what you created in your mind. You didn't write it down probably, but it's what you created in your mind looking at the problems in the last section. You said, oh, look, it's skipping every time by fives. I know what comes next. It's 5 more than the one before. It's a recursive pattern. You needed a few numbers in order to make that observation, right? And then you sort of guessed as to what would come next. It was your conjecture, and you were using inductive reasoning to make that assumption. That's what you were using. Observation of patterns, you assumed what happens next. The nth or the general term, this actually goes along with deductive reasoning. It's a formula that's used to find the nth term in the sequence and with no prior terms needed. You've done this in algebra. I know you've all had some algebra course somewhere along the way. And they gave you an equation. It said 4x plus 2, y equals 4x plus 2. And they told you x equals 3, and they asked you what is y, and you plugged it in. You didn't have to care about what came before or after it. You were given a formula, and you were given a value to put into it. That's what this is like. When we talk about the nth or the general term, that's the idea. It's a formula that you are able to use to plug numbers into. All right, first type of sequence that we're going to see today is called an arithmetic sequence. And this is the kind of sequences we were seeing happen in the last section with the problems with Gauss. So in an arithmetic sequence, each term is obtained from the number before using addition or subtraction of a fixed number. We're going to do an example. So if we have the numbers 2, 6, 10, 14, and then it just went dot, dot, dot. What's the pattern? The recursive pattern, the formula, if you will, is that we're adding 4 each time to get the next term. That's arithmetic. We could flip it around. We could start with 14, go 14, 10, 6, 2, comma, dot, dot, dot. We could do it that way too. And then the common difference, or the value we would be changing by every time, would be subtracting 4. So the value would be minus 4. This value that we add, or the ability to subtract or add a negative, is called the common difference. It's the fixed number added to or subtracted from previous terms to get successive terms in an arithmetic sequence. What is the common difference above? What was it? Yeah, it was 4, or you could write down plus 4. The sign does matter. We were adding 4, so it is part of it. The common difference was 4. Okay, that's an arithmetic sequence. That's the first type of sequence you usually encounter with numbers. The second sequence that we're going to look at is called a geometric sequence. A geometric sequence is a sequence in which each successive term is obtained from the previous term by multiplication or division by a fixed number. We're doing multiplication or division. And we're going to do the example. 108, 36, 12, 4, dot, dot, dot. So your goal looking at this, and this is going to happen over and over again in this section, is to figure out how do I get from one term to the next. And most of the time I'm not going to tell you, hey, this is geometric, go looking for something to multiply or divide. You have to recognize that fact. Okay, what do you recognize in this one? How do you multiply or divide to get to the next term? What do? It's division by 3. Now, my sort of description that I've written down makes this sound a little bit confusing, so let me read it like it is, and then let me see if I can explain it in a little bit better light. Common ratio is this ability to move from term to term with multiplication or division. Okay? So we know this has the same common ratio because I multiply or divide by the same term to get from term to term. The common ratio, however, for this problem is not 3. It's actually 1/3 because we always state common ratio in terms of what's multiplied to get there. So if you divide by 3, it's the same as multiplying by 1/3. You guys remember that? So when we talk about the common ratio, we're talking about the multiplication factor. So if you don't like the divide, you might want to even kind of cross it out. It's really all about what we're multiplying by to actually get the thing we call common ratio. So that's 1/3 in this problem. Okay, you guys ready to take an example? Oh, we're not quite there. We have one more to look at. Sorry about that. All right. There's another sequence that shows up in this section. It's a good one. It is very prevalent in real life, and it has a very fun name. It's named after the gentleman, mathematician who discovered it. His name is Fibonacci. Okay, Fibonacci sequence is non-arithmetic, non-geometric, so it's neither of the ones we talked about. And it follows a different pattern, therefore, and it's common in nature. So what is this different common in nature pattern? What in the world is it? Well, let me write it down. I don't want to give you a minute. If you've seen this before, then you've sort of got a leg up on everybody else. So just don't spoil the fun. See if you can figure out what in the world is the pattern. And once you think you know it, tell me what you think the next term is. If you absolutely know it, hold tight for a second, okay? Let everybody try to see if they can figure out what the next one would be. Hannah was smiling at me because I think she's seen it before. Has anybody else seen this before enough that you absolutely know what it is? Okay, got a couple, Ashley. Does anybody who hasn't for sure seen this before think you might have a guess as to what the next one is? What do you think?
19.
You're close, not 19. What do you think, Lauren?
21.
21, is that what you're thinking? It is 21. Okay, so let's pause again. For those of you who aren't quite sure yet what the pattern is, see if that helps you to figure it out. Do you see it now? Okay, Ashley, why don't you tell me, what is the pattern? How do you get from term to term?
You take the two numbers before it, and then you add those together to get the next number.
Okay, so 21 was obtained by taking 8 plus 13. Okay, so if we did the next number in the sequence, we would take 13 plus 21, and we would get what? 43? 44? Sorry. I can't write it right. I'm sorry. 34? Is that right? Did I get those numbers right? 34? Okay. So you'll see these examples with nature, with tree rings and shells, and there's all sorts of cool posters you can see with Fibonacci stuff on them. All right, this feels like an oddly placed thing, but it needs to be in here so that we can talk about it with the next slide. This is the definition of exponents, basically. The definition of a to the n. If n is a natural number, and it's the exponent a to the n like that, this means a times a times a times a and so forth, n times. Just like in the last section, when we had repeated addition, it's multiplication, right? Well, repeated multiplication is exponents. And for now, we're going to define that if n equals 0, so we have an exponent of 0, then that value is actually 1. So 3 to the 0 is 1, 5 to the 0 is 1. In prop and stat reasoning, proportional and statistical reasoning, we actually talk about I show you exactly why that is, like I prove it for you. But that's not part of the curriculum in this particular section of the class. So, okay, so for right now, it's good enough for us. And I'll show you why we need this in a sec. Okay, so let's come over here. I have an example. We are supposed to find the next 3 terms in the sequence, decide if the sequence is arithmetic, geometric, or neither, and then find the nth or general term for the sequence. And I'm kind of particular on that one right there, on how I'd like to see you think it through. So I'll talk through about that. The first 2 parts are pretty straightforward. So take a moment, ignore part C, we're looking at A and B, finding numbers 1 and 2. I want you to write down the next 3 terms in your sequence. I want you to decide if the sequence is arithmetic or geometric. And I want you to look at a neighbor and confirm that you and that person have the same thing. Okay, so go ahead and take a couple minutes and do those parts. we're going to come back to part 3. Yeah, I'm going to show you on part 3 how to deal with part 3. It's different. Just parts 1 and 2 for parts A and B. Sounds like I'm coding something, or parts 1 and 2 for parts A and B. So everybody had a chance to show their work to somebody else, make sure that it matched? Check real quick, if not. Okay. What are the next 3 terms in the sequence for part A? Okay, I hear lots of the exact same things, so that's a good first place to start. 13, 16, 19. What's the pattern? I just mean generally. I didn't ask this in the process, but what is the pattern you're seeing? Adding 3 numbers, right? You're adding the number 3, yeah. So because that's your pattern, that should help you to answer part 2 of the question. What is this, arithmetic or geometric? It is arithmetic. Okay, we'll come back to part 3 in a minute. How about part B on the problem? What are the next 3 terms? Fantastic. And what was the pattern? Geometric. It was multiplying by what? Was it 2? Okay, so this first one was adding 3. We're going to need that in here in a second, so I'll write it down. And this one was multiplying. Let me not use a dot. Multiplying by 2. Okay, now we need to talk about how we make this equation, or this general term. I would be lying if I didn't tell you that there's a formula in your book. But I'd also be lying if I told you that memorizing formulas is something that I view as a positive experience for pretty much anybody. And the reason is because 6 months from now, you're not going to remember any of those formulas you memorized, right? My hope is that you remember some of the processes that we do, though. Oh, yeah, I remember we did this, and this is why, okay? So when I teach both of these 2 that I'm about to teach you right now, I teach it from that perspective, because I don't think memorizing formulas is a good use of your time or a long-term benefit to you, all right? So here's what you do with arithmetic. Okay, so these are 2 different processes for the problems. You recognized, because you guys told me, that this is adding 3 every time, right? So, adding 3 every time, what does that tell me? Well, what happened in the last section when we added something that was the same together a whole bunch of times? We got to a point where we had 100 plus 100 plus 100 plus, what did we do? We multiplied instead, right? Repeated addition, which is what arithmetic sequences are. Repeated addition is multiplication. So we're going to take this number that we've repeatedly multiplied by, repeatedly added with, and we're going to multiply by it. So we're going to write down 3n, because we are repeatedly adding 3 every time. 3 plus 3 plus 3 plus 3 plus 3 to get the next term. So far, so good. Repeated addition is multiplication. Whatever value comes next is the value that has to come next to give me the first term. Here's what I mean. If we plug in the number 1 for the first term, that just whatever comes first in our sequence, what do we get here? What is 3 times 1? 3. But my first term in my sequence is not a 3. It's a 1. So what I'm going to write next is whatever I need to add or subtract so that I get the right value as my first term. So what would I need to add or subtract here? Adding 1 would give me the number 4. 3 times 1 plus 1 would be 4. I want it to be 1. Minus 2 will do it. So if you notice now, if I put in the number 1, 3 times 1 is 3. Minus 2 is 1. And you can check to make sure it works by trying another term in the sequence. So this is the second term, the location it's in. Not its number, but it's the term number it is. It is the second term. So if I put in the number 2, 3 times 2 is 6, minus 2 is 4. And that's my term, isn't it? It is 4. We'll try one more just so you can see it's for real working, okay? 7, that's my third term, right? It's the third number in the sequence. 3 times 3 is 9, minus 2 is 7. It's a little bit guess and check. It's a little bit of that stuff we did in for the first part of section 1, section 1.1, right? We're determining it based on what it needs to be, and we're checking to make sure it works by trying a few of the values in the list. That's what we're doing. Does that make sense? You're going to practice that, and it's a little bit weird the first couple times you do it, but that's the way it works. The 3 came from the common difference, and the term at the end comes from observation, trial and error. Okay? All right, the next one. This one's not arithmetic, it's geometric. You guys told me that. You also told me you multiplied by 2 to get to the next term, right? Okay. All right, so on the last one, arithmetic, we had plus 3, plus 3, plus 3, plus 3. We had addition multiple times, which is otherwise known as multiplication. Now we have multiplication multiple times. When you multiply by the same number over and over and over and over and over again, what is that known as? That's exponentials, right? That's why we did that definition right there. We're multiplying by 2 a whole bunch of times. We're going to express that as an exponential or an exponent. So what's it going to look like? Well, the exponent is 2. I'm sorry, not the exponent. The base is 2 because we're multiplying multiple times by 2. And here's where the cool thing is. The exponent is always, and I'll tell you why again too in a sec, but let's just write it down. The exponent is always in minus 1. Always. Always in minus 1. So let's just say we stopped right there and we thought we were finished. What would happen? Well, if I put in n equal to 1, what's 1 minus 1? 0. What is 2 to the 0? 1. Is my first term 1? No, it's not. It's 3. So what do I need to do? Well, because we're doing geometric instead of arithmetic, it's multiplication. I multiply by 3. So how does it really work? Well, what really happens is whatever is in front comes from the first term. And here's why. Is because this n minus 1 automatically makes the exponent 0. It makes it my first term, which means it's multiplied by whatever is on the outside, in this case a 3, to give me my first term. And we can check. Let's put in n equal to 2. 2 minus 1 is 1. 2 to the 1 would be 2, and 2 times 3 is 6. So what I have? Sure enough, let's try one more. Let's try n equal to 3. 3 minus 1 would be 2. 2 squared would be 4, and 4 times 3 is 12. And that's my next term right there. Okay? That's where all those pieces are coming from. So the 3 at the beginning is the first term. The 2 inside is the common ratio. It's what I multiply by. What if it had been the 1/3 like I had over here? Over here I had this 1/3. Can I make it 1/3 inside there raised to the n minus 1? Sure, no problem. 1/3 can be raised to the n minus 1. It doesn't matter if it's a fraction. What if up here, this instead of been adding 3 every time, had been subtracting 3? Can I put it as -3 in? Sure, absolutely, no problem. Okay? So don't get sort of led astray in the fact that the only example I did had a positive or had a whole number instead of a fraction. That's okay, it's no problem. All right? And I think, let's answer this question, then we'll stop because we are out of time. Inductive or deductive reasoning? Flip back and look at them. Is this inductive or deductive reasoning? Nope. Yeah, that's a good description, Amy. It's inductive because we're assuming what comes next. We're taking a pattern and we're making some sort of a generalization, some sort of a guess as to what happens next in the pattern. That is inductive reasoning. Okay? And we'll stop there for today.